Hi, and welcome to Module 9.4 of Digital Signal Processing. In the previous module, we saw an interesting signaling scheme that allows us to increase the data rate while keeping the same probability of error for a given power constraint. The problem is that the efficient communication alphabet that we devised is complex valued, whereas we know that physical channels can only handle real values. So in this module, we'll see how to transmit and recover a complex valued symbol stream over a real valued channel. Then we will follow this with a concrete design example for the telephone channel. And finally, we will compare the performance of the system to the ultimate limit in data rate that is given us by Shannon's capacity formula. So let's review where we stand in terms of transmitter design. We have the user's bit stream that comes into the system. This is sent through a scrambler that makes sure that the resulting bit stream is equiprobable. The mapper will split the bit stream into m-bit chunks, and each chunk will be associated to a complex valued symbol. This will create a complex value sequence A of n, and to fit that over the bandwidth prescribed by the channel, we have to upsample it, which means inserting k-1 zeros after each symbol of the sequence, and then low passing the sequence with a filter with cutoff frequency pi over k. Now, the sequence B of n, the upsample sequence that now fits the bandwidth constraint, is a complex valued baseband signal. Graphically, you can show this if this is the bandwidth constraint of the channel, positive and negative frequencies. The sequence B of n is a baseband sequence whose bandwidth fits the bandwidth prescribed by the channel. So now the question is, how do we modulate this while also making the transmitted signal real and making it real in a way that we can retrieve it and reconstruct the baseband complex signal at the receiver? So the way it's done is very straightforward. We just take the real part of the baseband signal multiplied by e to the j omega c n, where omega c is the standard frequency of the bandwidth of the channel. If we work it out, the math is very simple. So we have the product, of course, of the real part and imaginary part of the baseband signal multiplied by cosine of omega c n plus j sine of omega c n. And the real part of this equation is simply the real part of the baseband signal multiplied by cosine of omega c n minus the imaginary part of the baseband signal multiplied by sine of omega c n. Now you see here we're multiplying each component, the real imaginary part of the baseband signal, by a carrier, and the two carriers are orthogonal to each other. So we have a cosine carrier and a sine carrier. Now these two carriers are orthogonal because they're shifted by a phase of 90 degrees. Now when two things are 90 degrees apart, they're said to be in quadrature. And so the first component of the signal will be called the in-phase part, and the second component, the one modulated by the sine, will be the quadrature part. And this is the nomenclature behind the acronym QAM. Okay, so now this signal S of n is clearly real, and our next step will be to show that if we receive this at the receiver, we will be able to recover B of n, the complex baseband signal. But before we do that, let's look at the modulation process in the frequency domain, because the intuition will help us understand why we can recover the baseband signal exactly at the receiver. So in the next few diagrams, we will show the spectra of BR and BI, the in-phase and quadrature components of the baseband signal. Let's assume for the sake of convenience that these spectra are purely real, and we will indicate real quantities with shades of blue and purely imaginary quantities with shades of pink. The math would stay the same for arbitrary spectra, but this assumption will allow us to draw a simpler picture. So if we start by plotting the spectrum of the real part of the baseband signal, let's assume it has a shape like this. Then we plot the spectrum of the imaginary part of the baseband signal, and let's assume that, again, it's a purely real spectrum, except that it has a slightly different shape. And these shapes are completely immaterial, they just help us see what happens during the modulation process. The real part is multiplied by a cosine of omega c n, and therefore a cosine modulation takes place. It is shifted left and right and centered in omega c. For the imaginary part of the baseband signal, the modulation takes place via cosine, and there's a change of sign involved. So the resulting spectrum will be purely imaginary, and it will be shifted at omega c and minus omega c with a change of sign in the negative part of the spectrum. And so this is the spectrum of the signal that we actually send over the real channel. As you can see, the signal is real, and indeed the spectrum has a Hermitian symmetry in the sense that its real part is symmetric and the imaginary part is antisymmetric. Okay, so now let's assume that the transmission goes well, and our job at the receiver is to recover the complex baseband signal. A naive approach, we try the usual method, which is multiplying the signal by the carrier. Well, in this case we have two carriers, the cosine and sine, so let's start by multiplying by the cosine. And so if we take S of n, which is the transmitted and then received signal, and we multiply it by cosine of omega Cn, what we obtain is Br, the real part of the baseband signal, multiplied by cosine square of omega Cn, minus Bi, the imaginary part of the baseband signal, multiplied by sine of omega Cn times cosine of omega Cn. Now we use some really basic trigonometry to express these functions as functions of 2 times omega Cn, so cosine square of omega Cn becomes 1 plus cosine of 2 omega Cn over 2, and sine of omega Cn cosine of omega Cn becomes sine of 2 omega Cn over 2. And if we rearrange the terms of this equation, we obtain 1/2 times the real part of the baseband signal plus 1/2 of a term that only contains carriers at twice omega Cn, which is really similar to the situation we had in the simple cosine modulation and demodulation for a real signal. Again, it's much more intuitive if we look at this in the frequency domain. And so this was the signal that was transmitted and then received. If we multiply this by cosine of omega Cn, we obtain 1/2 of the spectrum of the real part of the baseband signal, plus spurious components at twice the modulation frequency. Now we know what to do to get rid of the spurious components. We just use a low-pass filter. In this case, we can use, again, a raised cosine. When we use this, we have what is called a matched filter configuration, where we use the same filter at the receiver that we used at the transmitter. This filter will eliminate the components out of the baseband, and we will recover the original real part of the baseband signal. We can do exactly the same for the quadrature component, for the complex part of the baseband signal, and in this case we multiply the received signal by sine of omega Cn. And if we work out the math with simple trigonometry once again, we obtain minus 1/2 times the imaginary part of the baseband signal plus out-of-band components at twice the modulation frequency, which we can filter out with a low-pass filter. So, we have proven that we can recover the baseband signal even when the original baseband signal is complex. The final design for the transmitter is the following: bitstream, scrambler, mapper, upsampler. We multiply the upsample signal by e to the j omega Cn. We obtain a complex passband signal. We take the real part, and finally we have the sequence of samples that we can send to the D2A converter and then over onto the channel. The receiver will receive the analog signal over the channel, will sample it at the proper sampling rate, and then demodulate it. So the signal is split into 2 parts that are identical. The first copy will be multiplied by cosine of omega Cn, and the second copy will be multiplied by sine of omega Cn. Both will go through a low-pass filter that is really the matched filter of the upsampling filter we used at the transmitter. And this will give us the real part of the original baseband signal and the imaginary part of the original baseband signal. We multiply this by j, we sum them together, and now we have the baseband signal, which will go through a downsampler. We keep one sample out, k, and this will give us the estimated symbol sequence created by the transmitter. The slicer will find the closest alphabet symbol and recover the chunk of m bits associated to the symbol, and finally the descrambler will undo the randomization and recover the original user data stream. So let's see how we can put everything we've learned so far together and design a practical system to send data over the telephone channel. Suppose that the bandwidth constraint for the telephone channel stipulates that we can only transmit data from 450 Hz to 2850 Hz. This gives us a usable bandwidth W of 2400 Hz with a sender frequency Fc of 1650 Hz. Now remember, in our all digital paradigm, we have to pick a sampling frequency that is at least twice the highest frequency there. So F max times 2, this would give us a sampling frequency of at least 5,700 Hz. But also, we're going to use an upsampling factor, which is an integer, and the trick is to pick a sampling frequency, which is an integer multiple of the bandwidth. So if we pick the multiple equal to 3, then we get a sampling frequency of 7,200 Hz, which of course satisfies the Nyquist criterion. When we translate the specs into the digital domain, we find that the modulating frequency is 0.458 pi. Now let's tackle the power constraint and assume that the telephone line has a maximum SNR of 22 dBs. You have to pick a probability of error that you can live with, and let's say that we pick 10 to the minus 6. If we use QAM, we can use the formula that we saw in the previous module to find the size of the alphabet, or alternatively, the number of bits per symbol that we can send. And the formula is this one, and when we plug in the values for the probability of error and the signal-to-noise ratio, we find that we can send at least 4 bits per symbol. And with 4 bits per symbol, we will have a constellation of 16 points. So that would look like this. The final data rate, remember, is the baud rate times the bits per symbol. The baud rate is equal to the bandwidth, so 2400, and so we have a total of 9600 bits per second. This is actually an operating mode of a modem standard called V24 that was popular in the 90s and that is still sometimes used in fax machines. Now the question is, are we doing good with respect to the maximum amount of information that we can send over this channel? Remember, we use very specific design choices to derive this figure of 9600 bits per second, a specific modulation scheme, a specific probability of error, and so on and so forth. What is the best one can do? Well, this is a complex question, and an exhaustive answer would require several lectures in information theory. But there is a formula derived by Claude Shannon in the late 1940s that states the capacity of a channel given its bandwidth and its signal-to-noise ratio. And this capacity specifies the amount of information that we can send reliably, meaning with an arbitrarily low probability of error, over a channel. The formula, unfortunately, is not constructive. It doesn't tell us how to send this data, but gives an upper bound on the amount of information that can be sent over the channel. So, for instance, for the parameters that we used before, the maximum capacity for that channel would be 17,500 bits per second. And with our design scheme, we're basically hitting half the capacity of the channel. The gap can be narrowed if we use more sophisticated modulation and data coding techniques, but as I said, to explore these topics, we would have to start an entirely new class in information theory.